Hey, it's chapter 10 time. This is inferential statistics, and it's all about null hypothesis and alternate hypothesis. So the idea here is that we want to test a hypothesis. This is a scientific method, baby. But the idea is that we start off with a null hypothesis, which we say is H naught. And let's just say that we say, oh, the population proportion is, 50-50, 0.5. It's like 1 out of 2 people have this thing going on. And then somebody does some sampling and checks it out and goes, you know what? I think that that's not true. I think it's possible that the population proportion is actually bigger than 0.5, right? I think that's true. So we create a statement that should be true, but then we create a statement we think is true. And that's how you differentiate between what is a null hypothesis and what is an alternate hypothesis. Now, the thing is, this is assumed to be true unless we prove that we can reject it. And we do that using statistics, which is great. Now, some of the formulas you're going to have to remember is how to find a z-score, because all of these are going to be normally distributed. So your z-score is always going to be the thing you find minus their proportion, the assumed proportion, so p hat. And that's over the sigma, which is p hat times 1 minus p hat all over n. Right? These are formulas from previous chapters. And this one I think is from chapter 7. And you can also see it in the chapter 9 formulas. But that's how we would find the z-score that we're going to look up. And with this z-score, we'll find the probability that your z-score is, let me call this z-hat, that your z-score is less than the one you found, or greater than, it's greater than, matches. And then that will be equal to the p-value. And then the p-value is compared to your alpha, your level of significance. So if your p-value is less than alpha, then we reject the null hypothesis. And that's the basics of testing a null hypothesis and an alternate hypothesis. We find the z-score, we find the probability using the chart, and then that's our p-value, and then we check it to alpha, which is usually like 0.05. And if it's less than, we reject it, and if it's bigger than 0.05, then we fail to reject. Now, that doesn't mean that the null hypothesis is true. It just means that in our sample, we don't have a significant enough sample to see that it's not true. So we just fail to reject it. It could be true, might not be true. I don't know. But I just know that this particular sample is not significant. Okay? So that's all just sort of a review of what's going on in chapter 10. Now, the first few questions is all like theory questions. So if we reject the null hypothesis when it's true, we've made an error. So here's this little chart, maybe that might help. And that is that we say, in this case, we reject or we fail to reject. Those are our two choices, right? And then in each of these rows, we have that the null hypothesis is true or that the null hypothesis is not true, it's false. Okay, so if we reject it when it's true, that is type 1 error. Type 1, you get it, whatever. And that's usually the probability of making type 1 error is alpha. If we reject it when the null hypothesis is false, then that's good, correct. If we fail to reject it when it's true, then that's good too, that's correct. And if we fail to reject it when it's false, that's what we call type 2 error. We made an error, and that's type 2 error. And that usually, the probability of finding type 2 error is usually referred to as beta. So that's the idea behind what type 1 and type 2 error is. We reject it when it's true as type 1. We fail to reject when it's false as type 2. And that's how I remember. I say reject type 1, fail to reject type 2. All right. Now, so when we start doing these problems, number 1 says if we reject when it's true, we've made a type 1 error. That's D. If number 2 is if we do not reject when it's in error, when it's not true, then we've made a type 2 error. So number 1 is type 1, D. Number 2 is type 2, C. Number 3, the level of significance is the probability of making type 1 error. So just so you know that, alpha is the probability of type 1 error. And beta is the probability of type 2 error. Now beta has a name, but we don't look at it very often. Alpha is usually called level of significance, and that is something that we do look at very often. I forget what beta is called. It's in the notes probably, or in the book. I really should look that up. Anyway, just for trivia's sake, number 4 starts to say, okay, now that we understand the basics, for number 3 is alpha. Number 4, now we understand the basics, let's really put this into context. So we have a problem where the average age of principals in a local school district is 46.8 years. So what they're saying is that the average age, or the mean, is 46.8. And if a hypothesis test is performed, how should you interpret a decision that rejects the null hypothesis? So if we figure out that this null hypothesis is rejected, then we're saying that it's not equal to 46.8, right? But more than anything, we say there is sufficient evidence to reject the claim. That's D. So sufficient evidence to reject the claim. So it's like if you reject, what really you're saying is there is sufficient evidence to reject. Now, we're not saying that rejecting is correct or that it's incorrect. What we're saying is that there's sufficient evidence that says you should reject the null hypothesis if you want to be more accurate in what you're talking about. So like somebody's like, hey, I think the average age is 46.8 years. And then you do some stats work, some inferential statistics, and then you go, yeah, I have enough evidence that says that that's not right. And they could take that and go, you know what? Okay, I'll correct my statement. Or they'll go, you know what? I don't believe in science, so I'm just going to keep what I said. And that's Facebook. Anyway, well, really, if you're in the scientific community, somebody, when they get sufficient evidence to reject a null hypothesis, they really should do that. And that's because lives are at stake normally. All right, so a survey claims, this is number 5, that 9 out of 10 doctors recommend brand Z. Have you ever heard that commercial? 9 out of 10 dentists. 2 out of 3 dentists. Anyway, this is 9 out of 10 doctors recommend this for patients who have children. So they said to test this claim, so their null hypothesis is that the percentage, the population proportion, is 90% or 0.9. 9 out of 10, right? So then it says, okay, test this claim against the alternative that the actual proportion is less than. So somebody believes, hey, I think it's less than. So then you would say that p hat is less than 0.9. That's the alternate hypothesis. Okay, so just get in the habit of writing your null hypothesis and your alternate hypothesis with numbers and letters like this, because that's going to help us do the rest of this business later. Okay, so then it says a random sample of 100 doctors gets 86 who indicate they would recommend it. And so we have a little p-value, not p-value, this is the proportion in our sample. So I don't know what you want to call it, like p sub 0 or something. Or I think the notes actually switch these two notations. It doesn't matter. The point is you have 86 out of 100, which is 0.86. Now what we're going to do is we're going to test that guy. And we do some testing, And we need to find a test statistic for this. So the idea here is we're going to use that z-score because this is a normally distributed group of people. We have 100 doctors, the p is 90% and the 1 minus p is 10%. So if you want to really check, you would say is it normal? You don't have to do this. I'm just trying to help you understand the process in the real world, what you would do. And you would say, okay, you got 100 doctors, the probability is 0.9, the thing that we assume, and then 1 minus p is 0.1. And if that's bigger than 10, it should work out. Well, this is actually 9, right? 0.9 times 100 is 90, and then 90 times 0.1 is 9. But it's really close to 10, and I think what they really want you to do is use normal. Really what you would use a t-score in this in the real world, but I think for this purposes of this, they didn't check this whole business. So anyways, we got 0.86, the thing you found, minus the thing that they're claiming. And that's going to be over the square root of 0.9 times 0.1, which is 1 minus 0.9, over n, which is 100. So in this case, what I would say is that like 100 is not a big enough sample, really, to use the z-score in this case. And then I think for the later with 10.4, we'll look at what else we can use if it's not a big enough sample. T-statistic. Anyway, so in this case, when I figure out this, it's 0.04, negative 0.04, that matters. And then this is, I don't know, 0.09 and then 0.0009, and that's reduced to 0.03. And then this reduces to negative 1.33333333. So it's B. Let me check that and make sure I did that in my head correctly. Yep, B. Okay. All right, so that's just one problem that asks you, hey, figure out the z-score using that little formula that we have right here. Okay. Now, number 6 and 7 ask you to actually write the null hypothesis and the alternate hypothesis. So let's do that on the same page. So number 6 says the mean, the average annual return for employees' IRA is at most 5.1%. So our null hypothesis, and I don't know if you know this, but if it's mean, we use mu, and it's always equal. So it's always equal when we talk about null hypothesis. Let me see if that's what they put. Just make sure. Yep. That's what I was taught. Because that's the idea that it's 5.1%. And what we can do is, if their claim is that it's at most a certain, then our alternate hypothesis has to be on the other side of it. So if they say if it's at most, that means that that's the biggest it can be, then our claim is that it's bigger than that. Right? Okay, so that's looking at what they say and us saying, no, that's not right, it's this, That's how we figure out the null and alternate hypothesis. And I think when they wrote their answer, they put, less than 5.1. I may have screwed that up, hold on. The mean is at most. If the mean is at most, that means it's less than. So they screwed up with their answer, I believe. I know, I don't want to say like, but honestly they did. If they're saying it's at most, that means it's less than, and we're going to say it's bigger than, right? All right. And then we say, okay, number 7, the mean utility bill. So again, the null hypothesis is a mean equal to, because it's always equal, and it says 101. So it says the mean utility bill in one city during the summer was less than 101. Okay, so I think what they're asking you to do is you're noticing something, and so your alternate hypothesis is going to be that thing that you're noticing. I think, because I think the answer for number 7 is this. Yeah. Okay, that's why I was confused. So yeah, so this is less than because you've noticed that it's less than this amount. So the null hypothesis is that it is this amount, and then you're saying, no, I think it's less than. Here, it's at most 5.1%, and they're saying it's 5.1. So you're going to say, no, I think it's less than, because, you know, I'm noticing it's at most this. That means that sometimes it's less than. So let's look at this as the alternate hypothesis, less than, okay? So sorry about the confusion on that, 6 and 7. I think the way they worded it confused me, but what they're saying is they say, here, you noticed something, so let's make that our alternate hypothesis. The null hypothesis is always the equal. Okay? Number 8 asks you to talk about type 1 and type 2 errors within the context of a problem. So we got to write their null and alternate hypothesis again. Some people use H1, by the way. I don't know. Doesn't matter. So they say the mean cost of textbooks for one class is greater than 150. So they're saying that the mean is actually 150, and I'm noticing that it's bigger than that. So my alternate is going to be bigger than 150, okay? And so if that's the case, then type 1 error will be rejecting the null hypothesis, that rejecting the fact that mu is equal to 150 when it is. When it is 150. That would be type 1 error. That's saying, hey, no, I think it's bigger. And when it's actually not bigger, then you've made a mistake, and that's a big mistake, type 1. And when it comes to like prices of a textbook, on average, it's not that bad of a mistake. But, you know, you still want to be correct, you know. And if you are going to be incorrect, then with your sample is not big enough, or it has a certain, you know, variability to it that makes it not sufficient enough to reject it, or it makes it sufficient enough to reject it, then, you know, it's a little bit of error, and that probability should be pretty low, right? And then the type 2 error is going to be failing to reject that mu is equal to 150 when it is bigger. It is greater than 150. So yeah, that's the idea, that we found it's actually bigger than 150, but when we did stats, we just failed to reject the null hypothesis that it is 150. What we're saying is that we couldn't figure out that it was bigger than 150 with our stats, with our sample. And that's type 2 error, and it's not a big deal in compared to type 1 error. If you ever want to get a good example of type 1 and type 2, and which is worse, think about the justice system. So type 1, we assume that somebody is innocent until proven guilty, right? We assume that they're not guilty until we actually prove that they're guilty. And so we have 4 choices there. We either have that they're guilty and we let them go free, and that's type 2 error. So we failed to reject the idea that they're innocent. So we ended up letting them out, letting them free. But the other one is, if we reject the claim that they're innocent, we find them guilty when they're actually innocent. That's locking up an innocent person, and that's, in our system, way worse than letting a guilty person out free. That's just, in my opinion, that's true, but it may not be your opinion, but that's the idea behind what the justice system is set up as. All right, number 9, same thing. You want to set up a null hypothesis and an alternate hypothesis. And the null says that the mean is equal to $96 for a monthly cell phone bill for one household. That's my monthly Actually, my monthly cell phone bill is a little bit bigger, and I needed to talk to Sprint about that because they suck. But, any other carrier in Oxford's also not very good coverage, so maybe AT&T, but they're also expensive and they suck too. I don't know. You tell me. Should I just get some sort of temporary phone? Landline? Should we go back to landlines? All right, but the alternate hypothesis, this says, is less than 96. So you're noticing that, hey, this is actually less than $96. So let's test this claim. The type 1 means that you're rejecting that mu is equal to $96 when it is. And then type 2, you fail to reject that mu is $96. So you think it actually is $96 when it actually is lower. when it's less than 96. Anyway, that's just an example of writing your null and alternate hypothesis and then telling me about type 1 and type 2. Now, I didn't put these in the quiz because I imagine you writing it out, typing it out, this stuff would either take a while because you have to mix in numbers and symbols with words, and plus some of you might not use the right language, but I'll still have to give you credit. So you know what, you get it. But null and alternate hypothesis, I think there are 2 questions where you do have to do that. Now we get to the fun part. We're going to test the claim. All right, we're going to do that thing we did earlier at the beginning of this. So we have that the claim is always the alternate hypothesis. And the claim is that the P is less than 0.85. 0. So that means that the null hypothesis is that it's equal to 0.850. Okay, so when we do this, we have n is equal to, let's just put a little box around that. We also have n is equal to 60. And then we have our observed, which is what they use for p hat instead of p. Well, I used p hat in the original example, but they've switched it up. Doesn't matter. You just have to, know what they're talking about when they use symbols. So 656 is actually their observed. And then this is the claim value. And so when we do a z-score for this, we're going to say the observed first minus the claim value, which is 0.850. And that's divided by the standard deviation with the claim value. So 0.850 times 1 minus that is 0.150. And that's all divided by n, which is 60. Okay. I need a calculator. Gonna bust out my computer calculator. Do. All right. So I've got to do this in my computer calculator, which is, 0.85 times 0.15 equals, and I'm going to divide that by 60 equals, and I'm going to take the square root of that, and that is going to be 0.0461. And then up here, when I subtract, I'm gonna add that to memory. And when I get 0.656 minus 0.850, and that's negative 0.194. And I'm going to divide that by my 0.0461, and that gives me a z-score. Oh my gosh, is that right? Negative 4.208. That's a huge z-score. All right. Well, I'm looking at what's going on to the left. So the idea is that the p-value I'm looking for is equal to the probability that my z-score is less than, because it's less than in the claim, negative 4.208. So then I go to my chart, right? Where's my chart? Dang it. Oh yeah, and I copied those charts, by the way. I put them into, what did I put them into? I put them in the module for week 4 in chapter 9. I put the normal in week 3's, I think. That's where normal first showed up. So you can print that off if you like. I have a file on my computer. Normal tables, here we go. I'm looking for negative 4.208, and look, the lowest number on the z-score is negative 3.49. So in this case, basically the p-value is 0. It's that close to 0. And yeah, that's less than 0.05, which is the claim alpha, which is what use alpha equal to 0.05. So yeah, so we reject H naught, the null hypothesis. Now I'm going to check, because that was a huge z-score. I'm going to just make sure Yep, I screwed that up. So nope. Negative 4.21, that's what they have. So you reject H naught. Okay? There is sufficient evidence to support the claim. So that's what we're seeing here, is there's sufficient evidence to support this claim that it's less than 0.85. Okay. Yeah, that was... Anytime you get a z-score that's off the chart, that is like a big indicator that you should reject. All right. H sub naught for number 11. The claim is that, you can start with the claim because that's what they write. The claim is that P is greater than or equal to 0.132. And so that means that H naught is that it's equal to 0.132. Right? So a little box around there, keep that there. And my N is 48. And my statistic that I found is 0.110. Sorry, statistic, my proportion. So again, we're going to do the z-score thing. The thing we found, 0.110 minus the claim value, 132. And that's going to be over square root of 0.132 times 1 minus 1.132, which is 0.868. And that's all over n, which is 48. All right, back to the calculator on my computer. Give me a second. Memory clear. So we're going to say 0.132 times 0.868 equals, divided by 48, 0.02387, and then we're going to take the square root of that, 0.048. So let's just write that. So we have it 0.04886. I don't know. If you want lots of decimals. The thing is, I'm saving this number with all of its decimal glory into the calculator so that I can just recall it and use it so I can be more accurate. This one up here, though, is 0.11 minus 0.132, and that's negative 0.022. So I'm going to divide that number by the 0.04886, and that is going to give me a z-score of negative 0.45. Not nearly as bad, right? So this number will have a p-value other than 0. So the p-value, though, is going to be the probability that z, oops, yeah, you know what I mean, probability of z is greater than, because it's this, negative 0.45. So I'm going to go to my chart, which I have up on my computer, and I go to 0.45, 0.4, and then go over to the 5 column, and that's 0.3264 on the left. So this needs to be 1 minus the probability that z is less than negative 0.45, and that's 1 minus the chart number, where'd my cursor go? 0.3264. Remember, greater than means 1 minus less than, because the chart is less than. In case you've forgotten, that's what it looks like. All right, so I got to subtract those two, and I'm going to get 0.6736. Okay, and then when I compare that to alpha, and the alpha, again, is 0.05, and that's bigger than 0.05. See, here it was less than 0.05, so we reject it. But when it's bigger than 0.05, we fail to reject. So what we found is that there is not sufficient evidence that our claim, or there's not sufficient evidence that we can reject this claim. Not that our claim is true or not. It might, I don't know, it might be true. But we don't have enough evidence to show that it is with this particular sample. We only picked 48 people, and we found their proportion to be pretty darn close to the actual claim. So because of that, you know, within a certain level of error, we don't reject this. You know, that's the idea. So we just have to keep going with that one statement without evidence to reject it. What I would do is I would just do another sample at that point, maybe with a bigger sample size. Airline claims that no-show rate is less than 5%. So the airline claims that it's less than 5%. So in our case, that's the claim. We are the airline. No-show rate. So let's say P is less than 0.05. We're going to change it to decimal when we use null and alternate hypothesis. So that means our null hypothesis is going to be that it's equal to 0.05. Okay. And then they took a sample of 420 randomly selected reservations, and 19 were no-shows. And so in this case, our P hat is going to be 19 over 420. Remember how we used to do that? We just took the number that was and we divided by the total. There you go. So 19 over 420 looks like it's going to be 19 divided by 420 equals 0.045. So we got 0.045, and we're going to find our z-score by using that 0.045 minus the claim value, which is 0.05, and we're going to divide it by the square root of 0.05 times 1 minus that, which is 0.95, divided by 420n. Okay, so back to the calculator. So 0.05 times 0.95 equals, divided by 420 equals square root. And I have on the bottom 0.0106 and some change, which I'm going to add to the memory. And then I'm going to say 0.045 minus 0.05 is negative 0.005. And now I'm going to divide that number by my 0.0106, and I'm going to get my z-score of negative 0.47. Okay, so the claim is less than, so my p-value, which I have to write out p-value because we're using p's all over the place, and it's not the same p as this. This is a different p, whatever. This is actually, p stands for power, by the way. That's why that p-value is that letter. But the p-value is the probability, and that's big P, so that's probability. So many p's. That z is less than negative 0.47. And we go to the chart, the table. And we go to 0.4, we go to the 7 column in the negatives. And that looks like 0.3192. All right, and we're testing this claim at 0.01. So 0.3192 is actually bigger than 0.01, isn't it? Yeah, it is. So again, we fail to reject. This sample tells us that there is not sufficient evidence to show that the null hypothesis is wrong. It might be wrong, but we don't know. There's not enough evidence, is what we're saying. Okay, recent study claimed that at least 15% were overweight. So at least is the claim, and that means bigger than, right? Yes. 15%, so P is bigger than or equal to at least 15%, so 0.15. Null hypothesis will be that it's equal to, it's always equal to. Shoop, shoop. Our N is 160, that's our sample of 160 students, and 18 were found to be overweight, so we put 18 over 160 and we get our discovered proportion. And that is 18 divided by 160 And that's 0.1125, right? So my z-score is going to be that thing, 0.1125, the thing I just found, minus the claim proportion. And then that's going to be divided by the square root of 0.15 times 1 minus 0.15, which is 0.85, divided by n, which is 160. And here we go again. So I'm going to clear that memory number. Let's do it. 0.15 times 0.85 equals, divided by 160 equals square root. And that gives me 0.02823. If you want that many decimals, I'm just going to save it. And plus, clear. And then I'm going to say 0.1125 minus 0.15 equals, and that's negative 0.0375. I'm going to divide that by our denominator, and I get a z-score of negative 1.328, which rounds to negative 1.33. Remember, z-scores need to just be 2 decimals. So my p-value is equal to the probability that my z-score is bigger than negative 1.33. Well, holy geez, yeah, it's going to be bigger than. I mean, maybe you don't understand how these numbers are, but as soon as I see that, I'm like, yeah. So this is 1 minus probability of z less than negative 1.33. So I go to my chart, table, negative 1.33, go to negative 1.3, go over to 3 column, and that is 0.0918. And it's 1 minus that, so it's really 0.9092, which is way bigger than 0.05. So we fail to reject. Fail to reject. I'm not checking these. I should check these. Oh, let me go down. All right, number 11. Where'd they go? Here we go. Let's see. Number 10, there is sufficient evidence to support the claim, which means reject. Number 11, there's not sufficient evidence, so fail to reject. Number 12, there is not sufficient evidence, so we fail to reject. They're not always writing the p-value. They sometimes do, but not always, right? That's weird. Number 11, they wrote the p-value. Number 12, they didn't write the p-value. That's okay. But you still fail to reject, and that's the whole point. And then number 13, they say there is not sufficient evidence, so we fail to reject once again. But they tell you the p-value. The p-value is 0.9092, 9082. You get what I'm saying. I can't subtract in my head sometimes. Okay. So far so good. We've been doing well. Number 14, last one. It's all by itself on that page. Engineering school or major university claims that 20% of its graduates are women. Ooh. So the claim is that it's 20%. Does this suggest that the school is believable? So basically what we're saying is that since the null hypothesis has to be equal to, we're saying that P is equal to 0.20, 20%. And in this case, since it doesn't matter if it's less than or greater than, which it has mattered in the past, we're going to say it's not equal to 0.20. And this is a two-tailed test. Two-tailed. So the idea is that once we find our z-score, that's a 2, not a z, 2. Once we find our z-score, we're going to find a p-value by adding the 2 areas, because under the normal curve, remember when it was less than, we just used the table number. When it was greater than, we would say 1 minus the table number. But when it's two-tailed, whatever z-score we find, you know, we're going to have to say that area times 2 because they're symmetric. So this area, which is, let's say A, we're going to say this is also A. So our p-value is going to be A plus A, or 2 times A. Okay? So just this is for a two-tailed test specifically. We've been doing one-tailed tests, so that's not really the same. All right, that's just there to keep you understanding how 14 is different. So they give you the N is 210 students, and they find that the proportion in this sample is 58 out of 210. So let's divide 58 divided by 210, and that is 0.276, okay, and some change. And if you want to, you can write it all out. If you 2609, that's fine. Anyway, but we want to find our z-score, and that is that number we just found, 27619, minus the claim value, which is 0.20, and that's going to be divided by the square root of 0.20 times 1 minus 0.20, which is 0.80, all divided by 210, the sample size. Here we go. 0.2 times 0.8 equals divided by 210 equals square root. That guy is 0.0276. And then we have the number we found, which is 58 divided by 210. Yeah, I had to do that again. And I'm going to subtract 0.2 from it, and I'm going to get 0.07619. Oh, I didn't save it. Dang it. Now I got to start over. 0.2 times 0.8, you can fast forward if you want, equals divided by 210 equals square root. Got the same thing. Now I'm going to save it. And then I'm going to say 58 divided by 210 minus 0.2, 0.07619. And I'm going to divide it by my saved number. And I'm going to get a z-score of 2.76, right? Cool. Okay, so when we look up this chart, this z-score is here and here. It's not a negative z-score, it's a positive z-score. So basically, I'm going to have to say that my p-value is going to be 2 times the probability, remember 2 times A, and that's the probability that my z-score is bigger than 2.76. So that's looking at this picture and making a statement that matches. You know what I'm saying? Okay. So I'm going to go to the chart, 2.76. I need that up. I got a negative chart. That's no good. I want the positives. I know you exist. Normal table. Nope, you don't exist. Okay. Let me go to my stats folder real quick. Stats. Let me find my normal table that I saved. Hopefully I saved one. There we go. Positives. All right, yeah, there we go. So we got my positives, 2.76. I'm going to go 2.7. I'm going to go all the way over the 6th column. And that is 0.9971. Wait, no, this is less than. So I had to say 1 minus the probability that z is less than 2.76. So this is 1 minus 0.9971. And if I were to say that, that's 0.0029. If I multiply that by 2, I get 0.0058. And I'm testing this against an alpha of 0.05. Well, this is smaller. 0.0058 is less than 0.05, right? So we reject. Rejection. Let me check number 14 down here. Yep, p-value is 0.0058. We reject. All right, that's how you do it. Okay, there it is.